In mathematics, spherical harmonics are the angular portion of a set of solutions to Laplace's equation. Represented in a system of spherical coordinates, Laplace's spherical harmonics are a specific set of spherical harmonics that forms an orthogonal system, first introduced by Pierre Simon de Laplace in 1782. Spherical harmonics are important in many theoretical and practical applications, particularly in the computation of atomic orbital electron configurations, representation of gravitational fields, geoids, and the magnetic fields of planetary bodies and stars, and characterization of the cosmic microwave background radiation. In 3D computer graphics, spherical harmonics play a special role in a wide variety of topics including indirect lighting and modeling of 3D shapes. History: spherical harmonics were first investigated in connection with the Newtonian potential of Newton's law of universal gravitation in 3 dimensions. In 1782, Pierre Simon de Laplace had, in his Ma copyright Conique car copyright list, determined that the gravitational potential at a point x associated to a set of point masses μ located at point psi was given by. Each term in the above summation is an individual Newtonian potential for a point mass. Just prior to that time, Adrien Marie Legendre had investigated the expansion of the Newtonian potential in powers of Ra equals ax and A1 equals ax1. He discovered that if Ra per mole current CO1 then, where I cubed is the angle between the vectors x and x1. The functions pi are the Legendre polynomials, and they are a special case of spherical harmonics. Subsequently, in his 1782 memoir, Laplace investigated these coefficients using spherical coordinates to represent the angle I cubed between x1 and x. In 1867, William Thomson and Peter Guthrie Tayet introduced the solid spherical harmonics in their treatise on natural philosophy, and also first introduced the name of spherical harmonics for these functions. The solid harmonics were homogeneous solutions of Laplace's equation. By examining Laplace's equation in spherical coordinates, Thomson and Tayet recovered Laplace's spherical harmonics. The term Laplace's coefficients was employed by William Whewell to describe the particular system of solutions introduced along these lines, whereas others reserved this designation for the zonal spherical harmonics that had properly been introduced by Laplace and Legendre. The 19th-century development of Fourier series made possible the solution of a wide variety of physical problems in rectangular domains, such as the solution of the heat equation and wave equation. This could be achieved by expansion of functions in series of trigonometric functions. Whereas the trigonometric functions in a Fourier series represent the fundamental modes of vibration in a string, the spherical harmonics represent the fundamental modes of vibration of a sphere in much the same way. Many aspects of the theory of Fourier series could be generalized by taking expansions in spherical harmonics rather than trigonometric functions. This was a boon for problems possessing spherical symmetry, such as those of celestial mechanics originally studied by Laplace and Legendre. The prevalence of spherical harmonics already in physics set the stage for their later importance in the 20th century birth of quantum mechanics. The spherical harmonics are eigenfunctions of the square of the orbital angular momentum operator. And therefore they represent the different quantized configurations of atomic orbitals. Laplace's spherical harmonics. Laplace's equation imposes that the divergence of the gradient of a scalar field f is zero. In spherical coordinates this is. Consider the problem of finding solutions of the form f, r, I, a equals r, y, I. By separation of variables, two differential equations result by imposing Laplace's equation. The second equation can be simplified under the assumption that y has the form y, a equals ai, I. Applying separation of variables again to the second equation gives way to the pair of differential equations. For some number m, a priori, m is a complex constant, but because I must be a periodic function whose period evenly divides to I m is necessarily an integer and I is a linear combination of the complex exponentials a plus or minus me. The solution function y, I, is regular at the poles of the sphere, where I equals 0, imposing this regularity in the solution I of the second equation at the boundary points of the domain as a Sturmer-Liouville problem that forces the parameter I to be of the form IA equals AA, A plus 1, for some non-negative integer with AAA permel beta m. This is also explained below in terms of the orbital angular momentum. Furthermore, a change of variable star equals Acasi transforms this equation into the Legendre equation, whose solution is a multiple of the associated Legendre polynomial. Finally, the equation for A has solutions of the form R equals R plus bra AA1, requiring the solution to be regular throughout R3 forces by equals A0. Here the solution was assumed to have the special form Y, A equals AI, I. For a given value of A, there are two A plus 1 independent solutions of this form, one for each integer m with AAA permel ma permel A. These angular solutions are a product of trigonometric functions, here represented as a complex exponential, and associated Legendre polynomials, which fulfill. Here is called a spherical harmonic function of degree A, and order m, is an associated Legendre polynomial, n is a normalization constant, and I represent colatitude and longitude, respectively. In particular, the colatitude I, or polar angle, ranges from 0 at the North Pole to I0 at the South Pole, assuming the value of I0/2 at the equator, and the longitude I, or azimuth, may assume all values with 0 AA permel IAA to I0. For a fixed integer A, every solution Y, I, of the eigenvalue problem is a linear combination of. In fact, for any such solution, Ra Y, I, is the expression in spherical coordinates of a homogeneous polynomial that is harmonic, and so counting dimensions shows that there are two A plus 1 linearly independent such polynomials. The general solution to Laplace's equation in a ball centered at the origin is a linear combination of the spherical harmonic functions multiplied by the appropriate scale factor R, where the R constants and the factors are known as solid harmonics. Such an expansion is valid in the ball. Orbital angular momentum. In quantum mechanics, Laplace's spherical harmonics are understood in terms of the orbital angular momentum. The is conventional in quantum mechanics. It is convenient to work in units in which the spherical harmonics are eigenfunctions of the square of the orbital angular momentum. Laplace's spherical harmonics are the joint eigenfunctions of the square of the orbital angular momentum and the generator of rotations about the azimuthal axis. These operators commute, and are densely defined self-adjoint operators on the Hilbert space of functions f² integrable with respect to the normal distribution on R3. Furthermore, L2 is a positive operator. If Y is a joint eigenfunction of L2 and Lz, then by definition, for some real numbers m and I, here m must in fact be an integer, for Y must be periodic in the coordinate I with period a number that evenly divides to I0. Furthermore, since and each of Lx, Li, Lz are self-adjoint, it follows that IAA permel beta m2. Denote this joint eigenspace by AE, M, and define the raising and lowering operators by. Then L plus and La commute with L2, and the Lie algebra generated by L plus, La, Lz is the special linear Lie algebra, with commutation relations. Thus L plus AE, M plus 1 and La AE, M Ma 1. In particular, Lk, plus AE, M plus k must be 0 for k sufficiently large, because the inequality IAA permel beta m2 must hold in each of the non-trivial joint eigenspaces. Let AE, m be a non-zero joint eigenfunction, and let k be the least integer such that. Then, since it follows that. Thus IA equals AA, A plus 1, for the positive integer A equals m plus k. Conventions. Orthogonality and normalization. Several different normalizations are in common use for the Laplace spherical harmonic functions. Throughout the section, we use the standard convention that, which is the natural normalization given by Rodrigues' formula. In seismology, the Laplace spherical harmonics are generally defined as, while in quantum mechanics, which are orthonormal, where IH is the Kronecker delta and D copyright equals SNI dd. This normalization is used in quantum mechanics because it ensures that probability is normalized, that is, the disciplines of geodesy and spectral analysis use, which possess unit power. The magnetics community, in contrast, uses Schmidt semi-normalized harmonics, which have the normalization. In quantum mechanics this normalization is sometimes used as well, and is named Ricard's normalization after Giulio Ricard. It can be shown that all of the above normalized spherical harmonic functions satisfy, where the superscript denotes complex conjugation. Alternatively, this equation follows from the relation of the spherical harmonic functions with the Wiener D matrix. Condorny-Euro-Shortly phase. One source of confusion with the definition of the spherical harmonic functions concerns a phase factor often for m greater than 0, one otherwise, commonly referred to as the Condorny-Euro-Shortly phase in the quantum mechanical literature. In the quantum mechanics community, it is common practice to either include this phase factor in the definition of the associated Legendre polynomials, or to append it to the definition of the spherical harmonic functions. There is no requirement to use the Condorny-Euro-Shortly phase in the definition of the spherical harmonic functions, but including it can simplify some quantum mechanical operations, especially the application of raising and lowering operators. The geodesy and magnetics communities never include the Condorny-Euro-Shortly phase factor in their definitions of the spherical harmonic functions nor in the ones of the associated Legendre polynomials. Real form. A real basis of spherical harmonics can be defined in terms of their complex analogues by setting. The Condon-Shortly phase convention is used here for consistency. The corresponding inverse equations are. The real spherical harmonics are sometimes known as tesseract spherical harmonics. These functions have the same orthonormality properties as the complex ones above. The harmonics with ma A0 are said to be of cosine type, and those with ma A0 of sine type. The reason for this can be seen by writing the functions in terms of the Legendre polynomials as. The same sine and cosine factors can be also seen in the following subsection that deals with the Cartesian representation. See here for a list of real spherical harmonics up to and including, which can be seen to be consistent with the output of the equations above. Using quantum chemistry, as is known from the analytic solutions for the hydrogen atom, the eigenfunctions of the angular part of the wave function are spherical harmonics. However, the solutions of the non-relativistic Schrödinger equation without magnetic terms can be made real. This is why the real forms are extensively used in basis functions for quantum chemistry, as the programs don't then need to use complex algebra. Here, it is important to note that the real functions span the same space as the complex ones would. For example, as can be seen from the table of spherical harmonics, the usual p functions are complex and mix-axis directions, but the real versions are essentially just x, y and z. Spherical harmonics in Cartesian form, the following expresses normalized spherical harmonics in Cartesian coordinates. And for m equals 0. Here. And. For this reduces to. Examples, using the expressions for, and listed explicitly above we obtain. It may be verified that this agrees with the function listed here and here. Real form, using the equations above to form the real spherical harmonics, it is seen that for only the terms are included, and for only the terms are included. And for m equals 0. Spherical harmonics expansion. The Laplace spherical harmonics form a complete set of orthonormal functions and thus form an orthonormal basis of the Hilbert space of square integrable functions. On the unit sphere, any square integrable function can thus be expanded as a linear combination of these. This expansion holds in the sense of mean square convergence Euro convergence in L2 of the sphere Euro, which is to say that the expansion coefficients are the analogues of Fourier coefficients, and can be obtained by multiplying the above equation by the complex conjugate of a spherical harmonic, integrating over the solid angle I copyright, and utilizing the above orthogonality relationships. This is justified rigorously by basic Hilbert space theory. For the case of orthonormalized harmonics, this gives: if the coefficients decay in a sufficiently rapidly for instance, exponentially then the series also converges uniformly to f. A square integrable function f can also be expanded in terms of the real harmonics above as a sum. The convergence of the series holds again in the same sense, but the benefit of the real expansion is that for real functions f the expansion coefficients become real. Spectrum analysis, power spectrum in signal processing. The total power of a function f is defined in the signal processing literature as the integral of the function squared, divided by the area of its domain. Using the orthonormality properties of the real unit power spherical harmonic functions, it is straightforward to verify that the total power of a function defined on the unit sphere is related to its spectral coefficients by a generalization of Parseval's theorem, where is defined as the angular power spectrum. In a similar manner, one can define the cross power of two functions as where is defined as the cross power spectrum. If the functions f and g have a zero mean, then SFF, A and SFG, represent the contributions to the function's variance and covariance for degree A, respectively. It is common that the power spectrum is well approximated by a power law of the form: when I squared A equals A0, the spectrum is white as each degree possesses equal power. When I squared AA0, the spectrum is termed red as there is more power at the low degrees with long wavelengths than higher degrees. Finally, when I squared AA0, the spectrum is termed blue. The condition on the order of growth of SFF, A is related to the order of differentiability of F in the next section. Differentiability properties. One can also understand the differentiability properties of the original function f in terms of the asymptotics of SFF, A. In particular, if SFF, A decays faster than any rational function of A as AAAAA, then f is infinitely differentiable. If, furthermore, SFF, A decays exponentially, then f is actually real analytic on the sphere. The general technique is to use the theory of Sobolev spaces. Statements relating the growth of the SFF, to differentiability are then similar to analogous results on the growth of the coefficients of Fourier series. Specifically, if then f is in the Sobolev space Hs, S2. In particular, the Sobolev embedding theorem implies that f is infinitely differentiable provided that for all s algebraic properties, addition theorem, a mathematical result of considerable interest and use is called the addition theorem for spherical harmonics. This is a generalization of the trigonometric identity, in which the role of the trigonometric functions appearing on the right-hand side is played by the spherical harmonics and that of the left-hand side is played by the Legendre polynomials. Consider two unit vectors x and y, having spherical coordinates and, respectively. The addition theorem states where power is the Legendre polynomial of degree A. This expression is valid for both real and complex harmonics. The result can be proven analytically, using the properties of the Poisson kernel in the unit ball, or geometrically by applying a rotation to the vector y so that it points along the z-axis, and then directly calculating the right-hand side. In particular, when z equals ay, this gives answer paragraph LD's theorem, which generalizes the identity cos 2ia plus a sin 2ia equals a1 to 2 dimensions. In the expansion, the left-hand side power, y, is a constant multiple of the degree a zonal spherical harmonic. From this perspective, one has the following generalization to higher dimensions. Let H be an arbitrary orthonormal basis of the space H of degree a spherical harmonics on the n-sphere. Then, the degree a zonal harmonic corresponding to the unit vector x, decomposes as. Furthermore, the zonal harmonic is given as a constant multiple of the appropriate Gegenbaur polynomial. Combining and gives in dimension I equals A2 when x and y are represented in spherical coordinates. Finally, evaluating at z equals ay gives the functional identity, where I per mil na1 is the volume of the sphere. Kleber-Gordon coefficients. the Kleber-Euro-Gordon coefficients are the coefficients appearing in the expansion of the product of two spherical harmonics in terms of spherical harmonics itself. A variety of techniques are available for doing essentially the same calculation, including the Wigner 3Jm symbol, the Ricard coefficients, and the Slater integrals. Abstractly, the Kleber-Euro-Gordon coefficients express the tensor product of two irreducible representations of the rotation group as a sum of irreducible representations. Suitably normalized, the coefficients are then the multiplicities. Parity. The spherical harmonics have well-defined parity in the sense that they are either even or odd with respect to reflection about the origin. Reflection about the origin is represented by the operator. For the spherical angles, this corresponds to the replacement. The associated Legendre polynomials give AZ plus M, and from the exponential function we have M, giving together for the spherical harmonics a parity offer. This remains true for spherical harmonics in higher dimensions. Applying a point reflection to a spherical harmonic of degree A changes the sign by a factor offer. Visualization of the spherical harmonics. The Laplace spherical harmonics can be visualized by considering their nodal lines, that is, the set of points on the sphere where, or alternatively where. Nodal lines are composed of circles, some are latitudes and others are longitudes. One can determine the number of nodal lines of each type by counting the number of zeros in the latitudinal and longitudinal directions independently. For the latitudinal direction, the real and imaginary components of the associated Legendre polynomials each possess AM zeros, whereas for the longitudinal direction, the trigonometric sin and cos functions possess 2M zeros. When the spherical harmonic order M is 0, the spherical harmonic functions do not depend upon longitude, and are referred to as zonal. Such spherical harmonics are a special case of zonal spherical functions. When AA equals AM, there are no zero crossings in latitude, and the functions are referred to as sectoral. For the other cases, the functions checker the sphere, and they are referred to as tesseral. More general spherical harmonics of degree A are not necessarily those of the Laplace basis, and their nodal sets can be of a fairly general kind. List of spherical harmonics. Analytic expressions for the first few orthonormalized Laplace spherical harmonics that use the Condon-Shortley phase convention. Higher dimensions, the classical spherical harmonics are defined as functions on the unit sphere S2 inside three-dimensional Euclidean space. Spherical harmonics can be generalized to higher dimensional Euclidean space Rn as follows. Let P denote the space of homogeneous polynomials of degree in n variables. That is, a polynomial P is in P provided that. Let O denote the subspace of P consisting of all harmonic polynomials. These are the solid spherical harmonics. Let H denote the space of functions on the unit sphere. Obtained by restriction from OR. The following properties hold. The sum of the spaces H is dense in the set of continuous functions on SNR1 with respect to the uniform topology, by the Stone-Weierstrass theorem. As a result, the sum of these spaces is also dense in the space L2, SNR1, of square integrable functions on the sphere. Thus every square integrable function on the sphere decomposes uniquely into a series of spherical harmonics, where the series converges in the L2 sense. For all phi A one has. Where I SNR1 is the Laplace-Euro-Beltrami operator on SNR1. This operator is the analog of the angular part of the Laplacian in 3 dimensions. To wit, the Laplacian in n dimensions decomposes as. It follows from the Stokes theorem and the preceding property that the spaces H are orthogonal with respect to the inner product from L2, SNR1. That is to say, for phi A H, and Ga ALHK for Kala Permel AA. Conversely, the spaces H are precisely the eigenspaces of I SNR1. In particular, an application of the spectral theorem to the Rice potential gives another proof that the spaces H are pairwise orthogonal and complete in L2, SNR1. Every homogeneous polynomial π can be uniquely written in the form where pjaa large. In particular, an orthogonal basis of spherical harmonics in higher dimensions can be constructed inductively by the method of separation of variables, by solving the Sturm-Liouville problem for the spherical Laplacian. Whereas the axial coordinate in a spherical coordinate system on SNA1. The end result of such a procedure is where the indices satisfy a 1 a per-mole currency, a 2 a per-mole currency. A per-mole currency in R1 and the eigenvalue is AA NR1, and R1 plus NR2. The functions in the product are defined in terms of the Legendre function. Connection with representation theory. The space H of spherical harmonics of degree A is a representation of the symmetry group of rotations around a point, and its double cover SU, 2. Indeed, rotations act on the two-dimensional sphere, and thus also on H by function composition. For IA spherical harmonic and IA rotation, the representation H is an irreducible representation of SO, 3. The elements of H arise as the restrictions to the sphere of elements of or harmonic polynomials homogeneous of degree on three-dimensional Euclidean space are 3. By polarization of IAA and OR, there are coefficients symmetric on the indices, uniquely determined by the requirement. The condition that IB harmonic is equivalent to the assertion that the tensor must be trace-free on every pair of indices. Thus as an irreducible representation of SO, 3, H is isomorphic to the space of traceless symmetric tensors of degree A. More generally, the analogous statements hold in higher dimensions. The space H of spherical harmonics on the n-sphere is the irreducible representation of SO, n plus 1, corresponding to the traceless symmetric tensors. However, whereas every irreducible tensor representation of SO, 2, and SO, 3, is of this kind, the special orthogonal groups in higher dimensions have additional irreducible representations that do not arise in this manner. The special orthogonal groups have additional spin representations that are not tensor representations, and are typically not spherical harmonics. An exception are the spin representation of SO, 3, strictly speaking these are representations of the double cover SU, 2, of SO, 3. In turn, SU, 2, is identified with a group of unit quaternions, and so coincides with the 3-sphere. The spaces of spherical harmonics on the 3-sphere are certain spin representations of SO, 3, with respect to the action by quaternionic multiplication. Generalizations. The angle-preserving symmetries of the 2-sphere are described by the group of Marr paragraph bias transformations PSL, 2, C. With respect to this group, the sphere is equivalent to the usual Riemann sphere. The group PSL, 2, C, is isomorphic to the Lorentz group, and its action on the 2-sphere agrees with the action of the Lorentz group on the celestial sphere in Minkowski space. The analog of the spherical harmonics for the Lorentz group is given by the hypergeometric series. Furthermore, the spherical harmonics can be re-expressed in terms of a hypergeometric series, as SO, 3, equals a PSU, 2, is a subgroup of PSL, 2, C. More generally, hypergeometric series can be generalized to describe the symmetries of any symmetric space. In particular, hypergeometric series can be developed for any Lie group. See also, cylindrical harmonics, spherical basis, spin spherical harmonics, spin-weighted spherical harmonics, Sturm-Liouville theory, table of spherical harmonics, vector spherical harmonics, notes. A historical account of various approaches to spherical harmonics in 3 dimensions can be found in Chapter 4 of Macrobot 1967. The term Laplace spherical harmonics is in common use. See Goron and Hilbert 1962 and Muger and Bauer 2004. The approach to spherical harmonics taken here is found in physical applications often take the solution that vanishes at infinity, making or equals A0. This does not affect the angular portion of the spherical harmonics. Edmonds 1957, A Section 2.5, Messiah, Albert. Quantum Mechanics 2 volumes bound as 1. Mineola, New York, Dover. ISBN A9780486409245 Al. Claude Cohen-Tarnauji, Bernard Dieu, Frank Lawlower. TRANSL. From the French by Susan Reed Hemley. A. Quantum mechanics. Wiley into science, Wiley. ISBN A9780471569527 Hirskalin and Moritz, Physical Geodesy, 1967, Eck. 1-62, Watson and Whittaker 1927, PA 392. This is valid for any orthonormal basis of spherical harmonics of degree A. For unit power harmonics it is necessary to remove the factor of 4 euro. Watson and Whittaker 1927, PA 395, Unser paragraph LD 1927, Stein and Weiss 1971, a section 4-2, Eremenko, Jacobson and Nadirashvili 2007, Solomontsev 2001. Stein and Weiss 1971, a section of 2, Higuchi, Atsushi. Symmetric tensor spherical harmonics on the N-sphere and their application to the de Sitter group SO, N, 1. Journal of Mathematical Physics 28 N. Vilenkin, Special Functions and the Theory of Group Representations, Math. Soc. TRANSL, Vol. 22. J. D. Talman, Special Functions, A Group Theoretic Approach. W. A. Benjamin, New York. W. Miller, Symmetry and Separation of Variables, Addison Wesley, Reading. A. Wozniak, Group Representations and Special Functions, Polish Scientific Publishers. Warsaw. References, cited references, Caron, Richard. Hilbert, David, Methods of Mathematical Physics, Volume I, Wiley into Science C. Edmonds, A.R., Angular Momentum in Quantum Mechanics, Princeton University Press, ISBN A0-691-07912-9. Eremenko, Alexander. Jacobson, Dmitry. Nadirashvili, Nikolai, on nodal sets and nodal domains on ZR² and Rankine squared, Université Copyright de Grenoble. Annals de l'Institut Fourier 57, 2345 Euro 2360, doi, 10.5802/AF 2335, ISNA 0373-0956, MRA 2394544, McRobert, T.M., Spherical Harmonics, An Elementary Treatise on Harmonic Functions, with Applications, Pergamon Pressa. Muger, Paul Hermann Ernst. Bauer, Edmund, Group Theory, The Application to Quantum Mechanics, Dover, ISBN A978-0-486-43798-9A. Solomontsev, E.D., Spherical Harmonics, in Haswinkel, Mikhail, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4A. Stein, Elias. Weiss, Guido, Introduction to Fourier Analysis on Euclidean Spaces, Princeton, New Jersey. Princeton University Press, ISBN A978-0-691-08078-9A. Unser paragraph LD, Albrecht, Beitragskurrency GE zur Quantenmechanik der Atom, Annalen der Physik 387, 355 Euro 393, Bibcode, 1927 and p. 387 355 U, doi, 10.1002/ANDP 19,273,870,304A. Watson, G.N. Whittaker, E.T., A Course of Modern Analysis, Cambridge University Press, PA 392A. General references, E. W. Hobson, The Theory of Spherical and Ellipsoidal Harmonics, Chelsea Pub Company, ISBN 978-0-8284-0104-3. Simar 1 Courtelaire, Spherical Harmonics, Springer, Lecture Notes in Mathematics, Volume 17, ISBN 978-3-540-03600-5. E. Condon and G. H. Shortley, The Theory of Atomic Spectra, Cambridge at the University Press, ISBN 0-521-09209-4, see Chapter 3. J. D. Jackson, Classical Electrodynamics, ISBN 0-471-30932-X, Albert Messiah, Quantum Mechanics, Volume 2. Dover. ISBN 0-486-40924-4. Press, W.H. Tucholsky, S.A. Bettling, W.T. Flannery, B.P., Section 6.7. Spherical Harmonics, Numerical Recipes, The Art of Scientific Computing, New York, Cambridge University Press, ISBN A978-0-521-88068-8, D. A. Varshalovich, A. N. Moskalov, V. K. Kosonsky. A Quantum Theory of Angular Momentum, 1988, World Scientific Publishing Company, Singapore, ISBN 9971-5-0107-4, Weierstein, Eric W., Spherical Harmonics, MathWorld.